Here the AK and the BK are the Fourier. AK and BK are the Fourier coefficients. So AK is given by f and cosine kx. That is 1 over pi minus pi fx cosine kx dx. So this is AK. Similarly, BK is f sine kx. That is 1 over pi minus pi fx sine kx dx. Okay, so and also A0 is 1 over pi minus pi fx, and maybe we should use this because the corresponding vector in the orthonormal system is 1 over square root of 2, but we will not use this. Our A0 is slightly different from the standard. We should remove the 1 over square root. Simply write this. Okay, and the half here is for simplicity of our later argument. Okay, so this is the Fourier series of periodic function which are square integrable in the interval minus pi to pi. Okay, so so this AK, BK, and A0 are Fourier coefficients of this function. But now this argument is applied for function f, for functions f belongs to L2. But even if f is only belong to L1, even if f belong to L, absolutely integrable, the Fourier series makes sense. If f is absolutely integrable, so this integral also converge. Therefore, AK is well defined. Similarly, BK is also well defined for every k, and including A0. So all the coefficients A0, AK, BK are all well defined. Therefore, we can still write the series on the right. We can still write this series. So this series is also called the Fourier series of f, and the AK, BK are called Fourier coefficients. Okay, so let's have a look on the basic property of the Fourier series and the Fourier coefficients. So we know that if f, by our Bessel inequality applied to this concrete situation, if f is in L2, then the Fourier series satisfies the following condition. By Bessel inequality, we have A0 square plus k equal to 1, AK square plus BK square will not greater than the norm of f square, that is f square x dx. Okay, so this is the particular Bessel inequality for our concrete function f. The Bessel inequality we have proved before. The Bessel inequality applied to any abstract general inner product space, as long as EI is an orthogonal system in X. We have this inequality. Okay, now apply this result to our X equal to L2. We obtain our concrete Bessel inequality in our situation. Okay, so from this Bessel inequality, we know that ak, that is 1 over pi minus pi fx cosine kx dx. This will goes to 0. Similarly, bk is also goes to 0. The sequence of bk also goes to 0. And why this goes to 0? Because the sequence ak square is converged. So as a converging sequence, as the general term of the convergent sequence, ak square must go to 0. Therefore, ak goes to 0. Okay. So if f belongs to L2, if f belongs to L2, we have Bessel inequality. Therefore, we can conclude that ak and bk goes to 0. But we will prove later that even if f only belongs to L, the result ak goes to 0 and bk goes to 0 are still true. This is the Riemann-Lebesgue lemma we will prove in our later video. Okay. Now, an interesting problem is that if f is L2, for f in L2, the bk square converge. Okay, so we know that bk also converge. Okay, why this converge? Why this converge? Because by the Cauchy-Schwarz inequality, the partial sum will not greater than bk square. Maybe not necessarily. Then this is finite because the sequence, the series sigma 1 over k square is converge. Okay, so this means for this is true for every n. So therefore, let n goes to infinity, we still have that the absolute value of bk over k, the series converge. So that is not every converging sequence, not every converging series can be not every converging trigonometric series can be Fourier series for a L2 function. The conclusion is that not all converging trigonometric series are Fourier series for some f in L2. We have a converging trigonometric series, but there is no f in L2, so that this trigonometric series is Fourier series. I will show you an example. So, example, there is no f in L2 whose f series is maybe there is no f in L2 such that the Fourier series of f is sine kx log k. There's no Fourier series such that is Fourier. There is no L2 function f such that its Fourier series is this trigonometric series. Why this is true? Using the Abel-Dirichlet theorem, you can prove that this is converge. This series converges. Okay, this series is convergent, but it could not be a Fourier series for any L2 function. No L2 function whose Fourier series is this trigonometric series, because this series that is not converge. If you have a f in L2, so that its Fourier series is this trigonometric series, then the coefficient that is bk here, because we only have sine, no cosine, so ak are all 0, we only have bk. Then bk must satisfy that this is finite. That the series bk over k is absolute value converge. But now for our this special bk is now 1 over log k. So for this bk, this series is not converge. It's not convergent. Okay, so this means that we cannot find an L2 function f whose Fourier series is the given series. Okay, now we have studied the Fourier series for function which periodic 2 pi. Okay, but sometimes we need to work with periodic functions which other periodics. Okay, so for 2t periodic function, we have studied the case t equal to pi. So we can consider the function defined minus t. Okay, then the corresponding orthonormal system is 2t 1 over square root cosine k pi x over t sine k pi x over t, also for k equal to 1 to infinity. So this is an orthonormal system of with respect to the inner product. For the square integrable function denoted by L2 minus t. For the square integrable function over the interval minus t, this is a vector space again, and we introduce this inner product. With respect to this inner product, we have the orthonormal system. That is the t2t consists of 1 over square root of 2 cosine k pi x over t sine k pi x over t for k from 1 to infinity. Okay, so using this as the orthonormal system, we have the Fourier series fx k from 1 ak cosine k pi x over t plus bk sine k pi x over t, where the a0 is 1 over t minus t fx dx, and ak is 1 over t minus minus t fx cosine k pi x over t dx, and the bk is 1 over t minus tt fx sine k pi x over t dx. Okay, so we can modify our previous argument slightly to obtain a similar result for our f, which is periodic 2t, not 2 pi. So the arguments are identical, are the same. The results are parallel. Then we have a similar result. Okay, or you can make a change of variable to change the 2t periodic function into 2 pi periodic function. And then every result we will establish can be carried over to the 2t periodic case. So we will not consider this anymore. In what follows, we only focus on 2 pi periodic functions. Okay.